Welcome to AI Frontiers. This special episode presents a snapshot analysis of robotics research. On December 31, 2025, researchers uploaded their final work to the arXiv preprint server. 15 papers from the foundational field of robotics, denoted by the academic category CS.RO, reveal the next frontier of embodied intelligence. This journey explores the crucial bridge between digital cognition and physical action in our messy, physical world. This presentation provides a blueprint for physical intelligence, mapping the research themes that will define robotics in 2026 and beyond. 5 dominant themes emerging from this single day's research will be explored. Groundbreaking findings that challenge conventional approaches will be discovered. The methodologies powering today's robotic breakthroughs will be examined. 3 seminal papers that map the field's immediate future will be spotlighted. The analysis concludes with clear directions for the next phase of embodied AI. Robotics represents the ultimate challenge of embodied intelligence, where digital algorithms must meet physical reality. The field moves beyond abstract reasoning to physical action in human environments. Key questions addressed include how robots learn complex manipulation and how they navigate uncertain, dynamic environments. This field builds the crucial bridge between cognition and action. The first research theme is whole body and dexterous manipulation, moving beyond simple pick and place to coordinated physical grace. Work by Hozichi and colleagues involves humanoid robots loading dishwashers with full body coordination. Sung Chae-min and team focus on lightweight robotic hands for practical humanoid applications. The core challenge is orchestrating head, hands, and legs for complex tasks. The goal is giving robots the physical capability humans take for granted. This represents a leap from isolated movements to integrated action. The second research theme is learning from demonstration and generative models, teaching robots through imitation and imagination. Karthik Dharmarajan and colleagues developed Dream 2 Flow, which uses generative video models as physics priors. Cheng Kai-ho and team created RoboMind 2.0, providing massive real-world demonstration datasets. The field is moving beyond painstaking programming to intuitive teaching methods. Generative models let robots learn from the imagination of possible actions. Massive datasets fuel the learning of complex manipulation skills. The third research theme is planning and control under uncertainty, navigating the messy, unpredictable real world. Kang Jia-jo and collaborators developed the Respire method for probabilistic search and tracking. Qian Cheng and team created the LSRE framework, which encodes social rules for autonomous driving. The real-world challenge involves noisy sensors, incomplete maps, and unpredictable agents. Solutions involve planning with educated guesses, not perfect knowledge. This includes encoding complex social rules into real-time decision systems. The fourth research theme is perception for functional understanding, moving from geometric vision to semantic and functional vision. Kuayu Yigu and colleagues built the RDSG system, which constructs functional 3D scene graphs. The goal is not just seeing a chair, but understanding sitability. It is not just seeing a drawer, but knowing it slides and in which direction. The system learns kinematic rules by watching human interactions. This turns static maps into interactive manuals for robots. The fifth research theme is efficiency and deployment on real hardware, the engineering crucible of making intelligence physical. Yi Chen Lu and others work on microrobot control on memory-constrained microcontrollers. Yang Sheng Zhao and team developed VLA Rail to handle asynchronous real-time systems. Xian Li and collaborators created CrapeSex for efficient multi-robot localization. The gritty reality is that algorithms must run unlimited onboard computers. This necessitates hardware-software co-design for practical, deployable systems. Key findings from these papers reveal 4 groundbreaking insights about the state of robotics. The choice policy architecture beats diffusion policies for humanoid manipulation. Generative video models successfully guide physical manipulation in a zero-shot manner. Semantic traffic rules are encoded into lightweight latent world models. Continuation-based learning bridges the simulation to reality gap for legged robots. These findings represent significant shifts in robotic learning approaches. The common methodologies, or the roboticist's toolkit, are synthesized across these papers. Imitation learning involves showing the robot what to do and letting it copy human expertise. Reinforcement learning serves as a trial-and-error engine for discovering novel solutions. Hierarchical planning is a divide-and-conquer strategy for complex tasks. Latent representation learning compresses sensor data for comprehension. Each method has distinct strengths and limitations for real-world deployment. The first selected paper is Coordinated Humanoid Manipulation with Choice Policies by Hosey Chi and colleagues, published in 2025. It was selected because it provides a complete blueprint for humanoid learning. Its innovation is a modular teleoperation interface for collecting complex demonstrations. A key finding is that the choice policy outperforms diffusion methods on real hardware. Its significance is a major leap from robots that merely walk to robots that can walk and work. The second selected paper is Dream 2 Flow, Bridging Video Generation and Open-World Manipulation with 3D Object Flow by Karthik Dharmarajan and team, published in 2025. It was selected for bridging the fundamental embodiment gap in AI. Its innovation uses 3D object flow as a bridge between video dreams and physical action. A key finding is zero-shot manipulation of rigid, articulated, and deformable objects. Its significance is as a general-purpose interface between generative models and robotics. The third selected paper is RoboMind 2.0, a multimodal, bimanual mobile manipulation dataset for generalizable embodied intelligence by Cheng Kai Ho and collaborators, published in 2025. It was selected for addressing the fundamental data bottleneck in robotics. Its scale is immense, with 310,000 real-world trajectories, 739 tasks, and 6 robot platforms. Its innovation includes tactile data, mobile manipulation, and digital twins. Its significance is as an ImageNet-like resource for the next generation of robot brains. Future directions for robotics, as illuminated by this research, are clear. There will be a deep integration of large foundation models into perception control loops. A massive push toward generalizable embodied intelligence is underway. The focus on efficiency and robust real-world deployment will only intensify. Advanced techniques will continue to bridge the simulation to reality gap. Growing research into the safety, reliability, and interpretability of autonomous systems is essential. This presentation was synthesized using the GPT DeepSeek model, specifically DeepSeek Chat. Text-to-speech synthesis was performed via Amazon Polly for audio narration. Image generation utilized OpenAI DALL-E for visual elements. Human expert review was conducted for accuracy and coherence. It is important to note that while reviewed, some oversights may exist. All references to the discussed papers are provided. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by the arXiv preprint server.